Hello everyone and welcome back. In the previous session, we learnt about the instruction types CMPR and CPID8, which provide the support for performing comparison between two operands. Now, if you have noticed carefully, the microprocessor 8085 not only has the instructions which help us perform the conventional logical operations like AND, OR, exclusive OR, and NOT, but also provides these type of instructions which help the developers perform something more. And from the previous session itself, we are learning about these unconventional instruction types. Continuing that streak, today we are going to learn about the instruction types RLC and RAL. So without any further ado, let's get to learning. Coming to the topics that we are going to cover in this session, today we are going to at first learn the instruction type RLC, and thereafter we will learn about the instruction type RAL. So let's begin with the first instruction type of the day, RLC. Coming to the instruction type RLC, it stands for rotate left accumulator and send a copy to the carry flag. Notice the mnemonic RLC. Here the letter R is coming from R of rotate, the letter L is coming from the letter L of left, and finally the letter C is taken from the C of copy. Now let me explain what this will actually do. In order to understand the working of the instruction RLC, first we need to understand this organization. As you can see, we have got a line from the accumulators this end, that is the most significant end, which is then connected to the least significant end, and if you notice the direction, it is from the most significant end towards the least significant end. Now if you notice this junction, the output line is also connected to the carry flag. Now what does it mean? We are supposed to rotate left the accumulator's content. So clearly, all the 8 bits of the accumulator will be shifted towards the left. And in that process, what will happen to the most significant bit? Well, the most significant bit will have to come out so that the rest of the bits can shift towards the left. And once the most significant bit is out, thereafter, if all the bits are shifted towards the left, by the end of the shifting process, there will be room available at the least significant bit's place. So that most significant bit, which we just brought out, will be now placed at the least significant place. And in that process, the most significant bit which came out, a copy of that will also be sent to the carry flag. Worry not, I'll explain the entire procedure with an illustration. For now, just remember the instruction RLC means we are supposed to rotate left the contents of the accumulator and in that process send a copy of the most significant bit to the carry flag. Now coming to the instruction RLC, it falls under the 1 byte long instructions category and it can be used for many things. At first, we can always use this instruction to check the value of the most significant bit. Now how we are going to do that? Think about it. I just told you about the process. All the 8 bits within the accumulator will be shifted to the left. In that process, the most significant bit will be shifted out and a copy of that will be sent to the carry flag. Now by the end of the process, although the most significant bit will become the least significant bit of the accumulator's content, but we still have a copy of that in the carry flag. So we can judge the content of the carry flag to figure out what was the value of the most significant bit. Apart from this, we can also perform multiplication by 2 by executing the instruction RLC. If you remember, when we were learning about the conversion from one number system to another, coming to binary, I told you in binary, shifting towards the left means multiplication by 2. Therefore, Execution of the instruction RLC one time means multiplication by 2. But if you execute the instruction multiple times, say 2 times, it will mean multiplication by 2 squared. That is, if we shift the bits towards the left only once, it is multiplication by 2 or 2 raised to the power 1. Now if we shift it twice, that will mean it is multiplication by 2 raised to the power 2 or 2 squared. So in order to perform multiplication by 2 raised to the power n, all we have to do is execute the instruction RLC n times. Let me now show you a practical illustration. Say within the accumulator we have got the value 24H. Now the 4-bit binary of 2 is 0010. What about the 4-bit binary of 4? It is 0100. Now within the accumulator we have got the hexadecimal value 24. Let's now execute the instruction RLC and allow me to show you what will happen by the end of the execution of the instruction. So as I told you, the most significant bit will come out and this event will make an empty space at the most significant bit's place. Now a copy of the most significant bit will be sent to the carry flag, and due to the space created by the absence of the most significant bit, all the rest of the bits will be shifted towards the left. And once the shifting is done, I told you earlier that there will be an empty space at the least significant bit's place. So the most significant bit which came out, which is 0 in this case, will now become the least significant bit. Now notice the contents of the accumulator. 0100, which is 4 in hexadecimal, and 1000, which happens to be 8. So after the execution of the instruction RLC, within the accumulator, we now have 48. So this was the content before the execution of RLC, and now this is the content of the accumulator, which is after the execution of the instruction RLC. Notice, 48 is twice of 24. Like I mentioned earlier, if we execute the instruction RLC once, it will mean we are multiplying with 2. But will it be same for all the cases? Well, no. Now let me illustrate that. I'll explain the reason for that by the end of the illustration. Say this time within the accumulator we have got the value 84. Now 8 in 4-bit binary is 1000. What about 4? It is 0100. So let's now execute the instruction RLC. This time the most significant bit which is coming out is 1. So we are going to send a copy of that to the carry flag. Now since the most significant bit's place is vacant, all the rest of the bits can be shifted towards the left by 1 bit. And by the end of this entire process, in the least significant bit, 1 will be placed, which was initially the most significant bit. Now notice the content of the accumulator. 0000 followed by 1001. Now 4 zeros is 0 in hexadecimal. What about 1001? It is 9. So within the accumulator, we now have the value 09. This is the content before RLC, and this is the content of the accumulator after the execution of the instruction RLC. Has it doubled? No, right? So the multiplication by 2 can only be performed if we are shifting the most significant bit, which is 0. If it is 1, then the logic of multiplication by 2 will not work. Try to understand this. If you notice the content within the accumulator right now, it is 0000 followed by 1001. Now if we talk about the bits with respect to place values, notice the place value of the least significant bit is 2 raised to the power 0 or 1. The place value of this bit is 2 raised to the power 1, which is 2, right? Coming to the next bit, the place value of this is 2 squared or 4. The place value of this bit is 2 cubed or 8. Now what is the place value of this bit? It is 2 raised to the power 4 or 16. Now think about it. If we perform RLC, the most significant bit currently is 0, so it will be placed as the least significant bit and the rest of the bits will be shifted by 1. So this one will come to this place, and I just told you the place value of this place is 16. Now what was the place value of the second place? It was 2. And after the execution of RLC, if the 1 of the least significant bit comes to this place, what will be the value inside the accumulator? Think about it. 16 plus 2, that is 18. If you notice, the most significant bit is 0, and when it got shifted to the least significant bit's place, at that moment, the bits within the accumulator got doubled. So clearly, if the most significant bit is 0, and thereafter we execute the instruction RLC, which will actually shift the bits within the accumulator towards the left, then only the contents inside the accumulator will be doubled. Another thing to notice in here, we call this bit the most significant bit. Now if we place a 1 in this place, that will carry the most of the value of the entire bit sequence. I hope you can understand the reason behind this. For the 8 bits that we have in here, the place value of the most significant bit is 2 raised to the power 7. So that actually carries the most of the value if we place a 1 underneath this place. Now if we shift that and say the next bit is 0, then we are turning the most significant bit's place to 0, which will then cancel out the entire value carried by the place value 2 raised to the power 7. And that's the reason why the instruction RLC won't be able to double the value within the accumulator register if we left shift 1, that is the most significant bit. I believe now it is clear to you. Anyway, the purpose of this instruction is mainly to check the most significant bit, and that is valid. Because by checking the content of the carry flag, after the execution of the instruction RLC, we can always make sure what was the most significant bit. Decisions during the program execution can be taken based on the contents of the most significant bit, a copy of which is now inside the carry flag. So do remember, the instruction type RLC stands for rotate left accumulator's content, and in that process, send a copy to the carry flag. So that was all about the first instruction type RLC. I hope you remember that this instruction falls under the 1 byte long instructions category. Let's now focus on the second instruction type of the day, RAL. Now coming to the instruction type RAL, it stands for rotate accumulator's content left involving the carry flag. Now if you remember, in case of RLC, we were just sending a copy to the carry flag. But this time, we are involving the carry flag. Notice the mnemonic RAL. Here, the letter R is coming from rotates R, A is coming from the A of accumulator, and finally, the letter L is coming from L of left. Now, in order to understand the working of this instruction, let's understand the organization first. Do you notice any differences with the previous organization? Well, this time, as you can see, we have got the most significant output connected to the carry flag, which in turn is connected to the least significant bit as an input. So clearly, when we execute the instruction RAL, the most significant bit will be sent to the carry, and the content of the carry by the end of the entire operation will become the least significant bit, because as we are shifting the most significant bit to the carry, the rest of the bits, since there is an absence of bit, can be shifted towards the left by 1 bit, which in turn will make an empty space at the least significant bit position, which will then be filled by the carry. So this is how we are involving the carry while rotating the contents of the accumulator. I am going to explain this entire process with an illustration, but for now, remember, RAL stands for rotate accumulator left involving the carry flag. Now the instruction RAL it also falls under the 1 byte long instructions category, and it can be used for checking the value of the MSB just like the previous instruction RLC, because here also we are sending the most significant bit to the carry flag. So by the end of the operation, if we check the contents of the carry flag, we will know what was the value of the most significant bit. That is, whether it was the bit 1 or the bit 0. Now this instruction RAL can also be used for performing multiplication by 2, just like RLC. But before we do that, we need to make sure of two things. The first thing is, the carry should include 0, because the bit 0 will then become the least significant bit. And another thing to notice in here, the most significant bit of the accumulator shouldn't be 1. If these two things have been taken care of, thereafter we can perform the multiplication by 2 using this instruction type RAL as well. But the question is, these two functionalities were also provided by the previous instruction RLC. Then why should we use the instruction RAL? Well, for that, I have got the third reason. We can introduce a new bit as the least significant bit. Think about it. Before the execution of the instruction RAL, say the carry flag is updated based on our requirement. In the previous sessions I have shown you, we can set the carry flag or complement the carry flag, or else using the instructions like STC and CMC in correct order, we can also reset the carry flag. So based on our desire, we can choose a bit which will be updated in the carry flag prior to the execution of the instruction RAL. And by the end of the execution of the instruction RAL, that bit will become the newly significant bit. This way, we can introduce a new bit as the least significant bit with the help of the instruction RAL. Let me now illustrate how this instruction is going to work. Say within the accumulator register, initially we have got the content 85. Now 8 in 4-bit binary is 1000. What about 5? It is 0101. Now before the execution of the instruction RAL, we should also update the carry flag with our desired bit, so that particular bit can become our newly significant bit within the content of the accumulator. And say for this, we are resetting the carry. So to be exact, within the accumulator we have got the 8 bits 10000 followed by 101, and within the carry flag we have got the bit 0. Now if we execute the instruction RAL, at first the most significant bit within the accumulator will come out, which in turn will make space at the most significant bit's place. Now this bit will then be placed inside the carry flag, and for that the carry flag's content will have to come out. Notice, the content of the carry flag was previously 0, now it is 1. That is, the most significant bit of the accumulator prior to the execution of the instruction RAL. Now the content of the carry, which was initially 0, will travel to the accumulator's least significant bit's place, and meanwhile the rest of the bits within the accumulator will be shifted towards the left one at a time. Notice, this process created an empty space by the least significant bit's place. So by the end of the operation, the bit 0, which was inside the carry flag initially, will now become the new least significant bit within the content of the accumulator. So after the execution of the instruction RAL, now within the accumulator we have got the value 0A. Why exactly 0A? Notice, 4 zeros is 0 in hexadecimal, and 1010, 10 of decimal, which in hexadecimal is A. Now what about the contents of the carry flag? Before the execution of RAL, it was 0, and now it is 1. So this is the outcome of the execution of the instruction RAL. With the help of this instruction, we introduce the newly significant bit 0 within the content of the accumulator. So clearly, This was the content of the accumulator and the status of the carry flag before the execution of RAL instruction. And this is now the content of the accumulator and the status of the carry flag after the execution of RAL. So that is all about the instruction type RAL. Do remember, the only difference between the instruction RLC and RAL is, in case of RAL, during the rotation of the accumulator's content to the left, we involve the carry flag. Whereas in case of RLC, we just send a copy of the most significant bit to the carry flag. We don't involve the carry flag in the process. So in this session, we covered the topics, the instruction type RLC and the instruction type RAL. Both the instructions fall under the 1 byte long instructions category. Alright people, that will be all for this session. In the next session, we are going to learn about a couple of more instruction types which involve the rotation of the contents of the accumulator. So I hope to see you in the next one. Thank you all for watching.